Hello everybody, my name is Devin Scallon, and in my presentation we will discuss serving the benthic community through Streambank restabilization and restoration on Powhite Creek, Virginia. The contents of this presentation will include an introduction in which we discuss the historic context and land use of Powhite Creek, the watershed response, modernization and effects on water quality, current restoration approaches, site constraints, stakeholders, and the restoration objective, followed by the study approach, results and discussion, conclusion, and references. Powhite Creek is a perennial flashy system that is 8 miles long and a first-order tributary of the James River in Chesterfield County, which empties at the south of Richmond in the region of the Fall Line. This entire area is encompassed within the Middle James River watershed located in the Piedmont region of Virginia. Chesterfield County was formerly known for its granite quarries and mill ponds, which were highly sought-after industries by blue-collar workers in the post-settlement era. However, these industries eventually led to the accumulation of legacy sediment, which buried natural floodplains. The region surrounding the mouth of Powhite Creek was formerly the unincorporated town known as Granite after these industries. However, as we will discuss, the removal of Petersburg granite seen in the two leftmost pictures on the James River changed the landscape forever. Evidence of these activities can be seen in the many gullies surrounding Powhite Creek, which suggest a historic landform that has been altered due to the presence of legacy sediment. The watershed response in a stream which was formerly known for its granite outcrops similar to those of the James is a channel comprised of fine-grained alluvium, a pool riffle-type planform, and evidence of severe bank instability and erosion, in which the primary sediment supply source are the stream banks. An initial site visit resulted in the following pictures as well as the observations that highly depositional features were apparent on the stream as well as little to no aquatic life. Returning to the modern era, as of 2000, the landscape surrounding Powhite Creek was approximately 90% urban land use, and in 2008, the Virginia Department of Environmental Quality determined that from its headwaters to its mouth at the James River, Powhite Creek is considered not supporting of the aquatic life use goal due to impairment of the benthic community. This means that the water quality indicator species determined by the EPT index are severely underrepresented with very limited biodiversity across all conducted assessments. To this day, Powhite Creek is listed on the Virginia 303D list of impaired waters under Category 5 for waters impaired or threatened by pollutants for one or more designated uses and requiring a maximum total daily load study. These disturbances are driven by the process of urbanization, in which stormwater runoff with sediment as a vector carries chemicals, nutrients, and bacteria from human activity directly to the channel. An additional effect of urbanization involves the inclusion of Powhite Creek as a receiving body to Chesterfield County's MS4 program, which discharges stormwater without treatment into local streams and rivers, and as a result, Powhite is now one of 5 streams monitored to evaluate conditions and assess long-term water quality trends as they may be related to this system. These monitoring reports include the following in-stream chemistry analyses for the years 2015 to 2020, in which the average total nitrogen is 0.8 milligrams per liter and the average total phosphorus is 0.1 milligrams per liter. Further research indicated that the U.S. Environmental Protection Agency developed ambient water quality criteria recommendations for streams and rivers under the Clean Water Act. For the aggregate ecoregion 9, which includes the Piedmont region of Virginia, the recommended total nitrogen limit was 0.69 milligrams per liter, and the recommended total phosphorus limit was 36.56 micrograms per liter. The conclusion is that the phosphorus amount exceeds the recommended amount nearly 3 times over for Powhite Creek. These reports also included bioassessments for benthic macroinvertebrates using the Virginia Stream Condition Index, which is a state-regulated water quality metric. Based on species richness and habitat score, these determined that severe environmental stress resulted in the stream being only partially supportive of the benthic community. In summation, the state of Powhite Creek is likely the result of extensive legacy sediment accumulation leading to downcutting and bank instability, and exacerbated by increased stream flow and nutrient input from current MS4 stormwater management practices. The current restoration approach is dictated by the MS4 program permit, which enforces minimum control measures, including public education and outreach, public involvement and participation, illicit discharge detection and elimination, construction site runoff, post-construction stormwater management, and pollution prevention and good housekeeping for municipal operations. In conjunction with this outline, we recommend a direct approach to stream restoration through the implementation of a channel design which complements source reductions in land-based best management practices by reconnecting the stream to its floodplain. It's important to recognize that in streams, up to 90% of transported phosphorus is attached to sediment, making erosion control one of the most important mitigation strategies against nutrient loading. Considering stream monitoring reports and current conditions of Powhite Creek, we believe that this should be the primary strategy to stream restoration. The inserted map includes the 0.5-mile restoration site of interest for Powhite Creek, in which the major site constraints for this area include a highway bordering the left bank of the stream, which will limit site design approach to channel slope, as well as residential areas to the south and east, as well as a recreational area that is often used for mountain biking and trail hiking along the creek. The design discharge and water quality will also be limited to the influence of the incoming flow from the MS4 system, and therefore will also limit the design of the stream. Even so, there are many parties with an invested interest in the restoration of Powhite Creek, including Chesterfield County and the City of Richmond, MS4 program affiliates, and local residents frequenting Powhite Park and the surrounding area, whether they be for financial, regulatory, or aesthetic and recreational purposes. Overall, the objective of this assessment is to determine the channel design that will stabilize the stream banks while maintaining sediment transport such that the aquatic life use goal of the benthic community is supported for Powhite Creek through sediment and nutrient loading remediation. To accomplish this goal, we recommend a multi-stage channel design including the bankful channel and floodplain benches with an inner berm. This design, according to the Iowa Department of Natural Resources, is allowed to accommodate a range of flows while maintaining sediment transport capacity, providing flood conveyance, reducing shear stress along the banks, and allowing vegetation to establish, as well as offering nutrient filtration through lateral floodplain connection. The bankful bench should transport the 1 to 2 year flood events, or bankful flow, before flooding occurs and without channel aggradation or degradation. To accomplish this, we must calculate the appropriate size and shape of the bankful channel accurately. We also note that currently there is no stream gauge data available for Powhite Creek. Therefore, the natural channel design approach using the reference reach method was used. To choose an appropriate reference reach, we use the Rosgen classification system to assess the current stream type of Powhite Creek. Using the Stream Stats elevation profile tool, a slope of 0.008 was estimated, with a moderate width to depth ratio, moderate sinuosity, and because of the current planform, an entrenched stream. A Woolman pebble count was conducted, in which the D50 or median grain size of the stream was assessed and determined to be approximately 16 millimeters. This concluded a Rosgen classification of F4 with characteristics including floodplain disconnection, bank instability, and pool riffle planform, which is consistent with the observations noted at the site. To estimate bankful characteristics, we use regional curves for the Virginia-Piedmont region, which assess bankful measurements according to the drainage area of a specific geographical region. For our site of interest, the drainage area was approximately 10 square miles and was determined appropriate because the stream HUC is included within the Piedmont location and the drainage basin area is less than 250 square miles, meaning the restoration site and regional curve references were consistent. Looking to our reference reach, Strubles Creek was listed for similar impairments due to similar environmental stressors and was restored using a two-stage channel design, allowing for the annual inundation of the lower bench by bankful flows and a high bench accessible to the 2.5-year recurrence interval floods. Because of Powhite Creek's floodplain disconnection, we recommend the restoration of Powhite from an F4 to a C4 system using native materials and multiple stages that encourage floodplain connectivity. We also want to note that because of the geographic difference between Strubles Creek and Powhite Creek, this design is only used as a guide and is not used directly for stream restoration. The results of our regional curve analysis for bankful flow resulted in a value of approximately 389 cubic feet per second. In addition, a regression model using the StreamStats water delineation tool was used for comparison of peak flow, in which the 42.9% AEP flood was determined as approximately 727 cubic feet per second. This highlights the statistical error in the estimation of bankful flow, and for consistency's sake, we continue with the regional curve analysis for all bankful conditions. The remaining regional curve analyses are included in the inserted table and compared to our reference reach site of Strubles Creek. A Manning's Inn of 0.04, side slope geometry of 2:1 for a trapezoidal channel, and a critical shields value of 0.045 were also determined for Powhite Creek and determined acceptable based on both Strubles Creek and the Rosgan C4 stream type classification. The application of the B-stem model also verified the effectiveness of streambank stability for all calculated parameters. Following the partial removal of legacy sediment, a final bankful channel of approximately 2.1 feet in depth, 34.8 feet in width, and with 2:1 side slope ratios will maintain the riffles of Powhite Creek. This bankful flow should reach the lower bench without imposing erosional forces on the banks, and the lower bench will be reestablished with native herbaceous vegetation and grasses, and the higher bench with native shrubs and woody plantings to reinforce nutrient filtration and stability. The inserted table on the left is an approximation of the current profile of Powhite Creek using the StreamStats elevation profile tool compared to the table on the right, which is an approximation of the stream profile according to the recommended restoration design. We recognize here that the proposed restoration design includes reducing the channel slope to 0.003 for a stable bankful flow. This design may or may not be possible in its entirety given the site constraints of an urban setting. In this case, we recommend further investigation into possible design options using channel-specific data that both maintain sediment transport capacity and allow for improved in-stream conditions while also compromising with limited channel settings. In conclusion, based on regional curve data for the Piedmont, Virginia region, reconstruction of Powhite Creek from an F4 to a C4 stream with a main channel width of 34.8 feet, a depth of 2.1 feet, and a decreased slope of 0.003 may allow for bankful flow that inundates the inset floodplain annually without exceeding bank critical shear stress. Here we include that future analyses should include bedload transport model to ensure minimal movement of the 84th percentile grain size. We also recommend an integrated solution including the application of watershed-scale stormwater best management practices through the County MS4 program as recommended previously. Post-project monitoring should also take place for at least 3 years to assess bank stability and sediment transport, as well as in-stream chemistry and species abundance analyses to determine the effectiveness of stream restoration. Here are several references that were used throughout this presentation. If there are any questions, please leave them below, and thank you for listening.